Right now, a fleet of NASA spacecraft are turning their attention to an unusual object speeding through our solar system.
The discovery that a large interstellar object, designated 3Y Atlas, is now projected on a collision course with Mars has set the astronomical community abuzz with urgency and intrigue. This is not merely another passing visitor from beyond our solar system, but a rare celestial wanderer that has entered with a trajectory unlike anything seen before. NASA and Harvard astronomers jointly confirmed that precise calculations of its orbit point toward a direct encounter with the red planet, a moment that could become one of the most consequential events in modern planetary science. The collision, if unaltered, represents a monumental opportunity for observation and understanding, as well as a stark reminder of the dynamic and unpredictable nature of our cosmic environment. Before we start, smash the like and subscribe buttons for more updates. Interstellar objects have long fascinated scientists, especially since the first known visitor, Nannen Oumuamua, swept past the Sun in 2017. That mysterious body carried with it questions about its origin, composition, and the mechanisms that propelled it across interstellar space. Later, 2I Borisov, a comet-like traveler, offered additional clues about material formed around distant stars. Now, with 3I Atlas, the story deepens further, not because it is simply passing through, but because it is on course to strike Mars. Such an event is not a distant abstraction. It is a real physical confrontation between a planet in our solar system and a messenger from the depths of the galaxy. The implications of this are vast, and ripple across fields from astronomy and planetary science to questions of planetary defense and cosmic history. The path of 3I Atlas was determined through painstaking work involving multiple observatories across the globe. At first, its approach appeared to mirror the arcs of prior interstellar bodies: a steep entry trajectory, rapid velocity, and a slingshot departure back into deep space. But as data accumulated, including measurements of its acceleration and the curvature of its path, a dramatic revelation emerged. Unlike its predecessors, this object was not bound to simply pass by. Instead, the gravitational pull of the Sun and Mars combined in such a way that the interstellar traveler's orbit tightened into a fateful line of impact. Astronomers initially met the finding with skepticism, but repeated refinements of the data confirmed the prediction. By consensus, NASA and Harvard researchers now agree. Unless some extraordinary natural perturbation alters its path, 3I Atlas will collide with Mars. The sheer scale of the event makes it impossible to overstate its importance. 3I Atlas is estimated to be several kilometers across, comparable in size to the asteroid thought to have struck Earth 66 million years ago, contributing to the end of the dinosaurs. A collision of such magnitude with Mars will unleash forces that could reshape parts of the Martian surface dramatically. Vast craters, seismic reverberations, and dust plumes extending into the thin atmosphere will all be immediate outcomes. The energies involved will be beyond anything human technology has produced, offering scientists a direct look at planetary scale impacts in real time, where Earth's geological record has long hidden the scars of its violent past. Mars, with its relatively static surface and thinner atmosphere, will preserve this new impact as a clear signature for eons to come. From the perspective of planetary geology, the collision presents a unique chance to study how celestial bodies respond to impacts. Mars already bears evidence of massive cratering from its past, but these occurred billions of years ago. To witness such a process unfolding now offers data that can refine theories of planetary formation, surface dynamics, and the role of impacts in shaping planetary environments. For instance, the composition of the dust cloud thrown into the Martian atmosphere could reveal buried layers of the crust not otherwise accessible. Instruments already orbiting the planet, including probes and satellites operated by NASA, ESA, and other agencies, will be poised to capture every moment of the event. Their readings will illuminate not only the destruction, but also the underlying geology exposed in the aftermath. The presence of interstellar material adds another layer of significance. 3I Atlas carries within it chemical signatures from a stellar nursery far from our Sun. This collision will quite literally fuse two worlds, the ancient Martian surface and matter forged around another star. Scientists anticipate that fragments of the impact may spread across the Martian landscape, embedding themselves in craters and dust layers. Future missions to Mars could retrieve these samples, offering direct evidence of the chemistry of distant systems. Such an opportunity to examine alien material delivered naturally to a neighboring planet is almost beyond belief. A serendipitous laboratory set up by the universe itself. The timing of this discovery is equally remarkable, given humanity's growing interest in Mars as both a scientific and exploratory target. With multiple rovers exploring its surface, orbiters scanning its terrain, and plans for future human missions under active development, the collision of 3I Atlas adds a dramatic twist to the Martian narrative. Scientists now face the prospect of incorporating this natural experiment into their exploration plans. The rovers, depending on their proximity to the impact site, could record seismic waves generated by the collision, capturing data that artificial instruments could never replicate. The orbiters, positioned strategically, may capture unprecedented high-resolution views of the impact and its spreading effects over time. Every element of Mars exploration now intersects with this extraordinary event. While excitement surges, there is also a sense of caution in how this knowledge is framed. Some wonder whether such an impact could alter the stability of Mars in ways not yet considered. Its thin atmosphere may react unpredictably to the injection of vast amounts of dust and vapor. There are even questions about whether subsurface ice deposits, when suddenly exposed and vaporized, might cause localized climate shifts or trigger cascading effects. Although these scenarios remain speculative, the very fact that they are on the table demonstrates how profoundly disruptive the collision could be for Mars as a planetary system. Scientists must balance the eagerness to observe with sober consideration of what long-term changes may follow. Another thread of inquiry arises from the velocity of 3I Atlas. As an interstellar object, it travels at extraordinary speed, far surpassing that of typical asteroids or comets native to the solar system. This immense velocity translates into collision energies orders of magnitude greater than even large impacts Earth has experienced. The shock waves, both in the crust and in the tenuous Martian atmosphere, will carry signatures unique to such high-speed interstellar collisions. Studying these signatures could refine our understanding of how energy dissipates in planetary environments and what thresholds exist for planetary-scale destruction versus mere transformation. In essence, Mars has become the stage for a natural experiment in astrophysics, geology, and planetary defense rolled into one. The planetary defense community is particularly attentive to this event. Although Mars is the target rather than Earth, the dynamics of 3I Atlas's path highlight how interstellar bodies can pose unanticipated risks. Traditional asteroid tracking systems focus on objects bound by the sun's gravity, whose paths can be projected with high confidence. But interstellar objects arriving at steep angles and high speeds challenge these frameworks. The confirmation of an actual impact within the solar system raises the stakes for developing detection methods capable of spotting such intruders earlier. It forces a reevaluation of whether humanity is adequately prepared to respond to the possibility, however rare, that one could be aimed at Earth instead. At the same time, philosophers and cultural commentators see symbolic weight in the impending Martian impact. To some, it underscores the fragility of worlds in the face of cosmic forces. To others, it is a reminder that planets, even those considered static or lifeless, remain active participants in the ongoing drama of the cosmos. The very idea that a piece of another star system will merge with Mars resonates on a level beyond science alone, touching themes of cosmic unity and the interconnectedness of all celestial bodies. For explorers and dreamers alike, it is a moment that binds the story of Mars more closely to the wider galaxy, reminding us that no planet exists in isolation. There is also a strong sense of urgency in preparing observational campaigns. Coordinated efforts are already underway between NASA, Harvard, and international institutions to deploy every available instrument toward Mars as the moment of impact approaches. Ground-based telescopes, space-based observatories, and planetary missions all contribute to what will likely be the most comprehensive dataset ever assembled for a planetary collision. This collaboration mirrors the global spirit that accompanies other great scientific endeavors, uniting countries and agencies in pursuit of understanding. The event transcends borders, belonging to all humanity as a shared opportunity to witness the power and mystery of the universe. The announcement that 3I Atlas is on course to strike Mars has ignited a cascade of new discussions across astronomy, planetary science, and space exploration. The sense of immediacy surrounding the event has grown because this is not a theoretical projection about something billions of years in the past, but a real collision happening within a time frame that living generations of scientists, engineers, and explorers will witness. Each discipline now approaches the subject with its own questions, theories, and preparations, and the sheer variety of angles through which this single cosmic event can be studied ensures that it will remain one of the most scrutinized episodes in planetary science for decades. The object's origins are as compelling as its destination. Being interstellar, 3I Atlas did not form in the disk of gas and dust that birthed the Sun and its planets. Instead, it is a fragment of another star system, ejected during the chaotic early epochs when new stars are often surrounded by swarms of planetesimals. The process of planetary system formation frequently involves gravitational tussles, close encounters, and violent ejections, with many bodies cast into the galactic void. 3. Atlas is one such wanderer, carrying the mineralogical and chemical record of a birthplace far beyond our solar neighborhood. Its collision with Mars therefore represents not just an astronomical encounter, but the physical merging of histories separated by light years of distance and eons of time. For researchers who study planetary genesis, this is as close to a gift as the cosmos can provide, a chance to see what other nurseries produce when compared to our own. Astrochemists are particularly eager to assess the composition of 3I Atlas once fragments or ejecta can be analyzed. Spectroscopic studies from Earth-based observatories already hint that it may contain unusual ratios of isotopes and compounds not commonly found in solar system asteroids. The impact will shatter, vaporize, and scatter parts of its body across Mars, embedding exotic elements within new geological layers. When future missions land near the site or sample atmospheric fallout, they may bring back evidence that broadens our knowledge of galactic chemistry. Questions about how common water-bearing or organic-rich bodies are in other stellar systems may find answers in the material scattered by this impact. It becomes a test case for evaluating the galactic distribution of life's building blocks. Dynamicists, those who model celestial motions, see in this event a perfect natural experiment for testing the limits of orbital prediction. The fact that 3I Atlas has been tracked with such precision, despite its high velocity and unusual entry path, demonstrates the advances made in astronomical computing and global observational networks. But the weeks and months leading to the collision will challenge these systems like never before, as tiny outgassing jets or microgravitational perturbations could create measurable shifts. Refining models against real-time updates allows scientists to improve the tools used to predict potentially hazardous objects. In this sense, Mars is acting as a proving ground not just for interplanetary geology, but also for planetary defense systems that one day might shield Earth. There is also the question of what the Martian surface and atmosphere will reveal in response to the impact. Unlike Earth, where weathering, tectonic shifts, and erosion erase craters over time, Mars preserves its scars for millions or billions of years. A fresh, large-scale crater from 3I Atlas will provide a pristine reference point to compare against older basins. This new site will become a benchmark for interpreting past Martian impacts, allowing geologists to calibrate erosion rates, dust layering, and atmospheric interactions. Even the pattern of ejecta, the spread of dust and rock around the impact site, will refine understanding of how material disperses in a low-pressure atmosphere. Mars is an ideal laboratory in this respect because its thin air slows material differently than Earth's thick envelope but does not allow the near-perfect vacuum dispersal that occurs on the Moon. For planetary seismologists, the collision offers what amounts to a natural megaton-scale seismic experiment. Mars has already yielded valuable data through the InSight lander, which recorded Mars quakes and meteorite impacts. But no human instrument has yet measured the seismic signature of a body as large and fast as 3I Atlas striking the crust. The energy transfer will be immense, and if seismic sensors still function on Mars, or if new ones can be positioned in time, they may capture readings that unlock hidden layers of the planet's interior. Seismic waves will ripple through the mantle and core, revealing boundaries, densities, and compositions with a clarity no artificial experiment could match. The knowledge gleaned would not just illuminate Mars but also enhance comparative planetology, sharpening models of how rocky worlds evolve. Another discipline watching closely is atmospheric science. While Mars has only about 1% the atmospheric pressure of Earth at the surface, the introduction of colossal quantities of dust and vapor will nonetheless alter its skies in dramatic ways. The plume from the impact may rise hundreds of kilometers, temporarily thickening the atmosphere in localized regions and scattering sunlight. This could change surface temperatures and winds on a short-term basis. Scientists hope to track these changes as a real-world analog for ancient events in Earth's past, when asteroid strikes may have thrown enough dust into the air to trigger temporary climate disruptions. Mars thus becomes a canvas for testing models of how planetary climates react to sudden extraterrestrial inputs, insights that may also apply to Earth and other potentially habitable planets. Engineers engaged in designing human habitats for Mars find themselves revisiting assumptions about safety and resilience. While the collision site itself may lie far from any intended landing zones, the dust it throws into the air could drift across the planet, depositing fine material that future equipment will have to endure. Solar panels, machinery joints, and habitat seals could all face unforeseen challenges if such an event occurred during human occupation. Even though the timeline for settlement may not coincide with the immediate aftermath of the impact, the lessons learned will influence design philosophies for decades. Mars is proving once again that its environment cannot be treated as static. Instead, it demands flexibility, redundancy, and foresight from those who plan to step onto its soil. For mission planners already considering sample return missions from Mars, the timing of 3I Atlas adds an enticing layer of possibility. A crater containing freshly exposed interstellar material would be a prime target for future landers or rovers. The mix of Martian geology with alien chemistry could provide the most extraordinary samples ever returned to Earth. The logistics of redirecting missions or designing new ones to specifically study the site are already topics of intense discussion. Agencies recognize that opportunities of this scale are once in a lifetime, and the scientific value could rival, if not surpass, the moon rocks brought back during the Apollo program. Each grain of dust from the impact would tell two stories at once: the story of Mars and the story of a distant star system. Beyond science and engineering, the impending event stirs profound cultural and philosophical contemplation. Humanity has always looked at Mars as a symbol of both war and exploration, a red beacon inspiring stories from myth to science fiction. The idea that this planet, so deeply woven into our imagination, will be struck by an object from another star evokes awe. Some view it as a cosmic performance, a reminder of the grand scale of processes that dwarf human concerns. Others see it as a warning, an omen of what could one day befall Earth. Such interpretations echo through literature, art, and public discourse, ensuring that the impact of 3I Atlas will not remain confined to academic circles. It will enter the shared cultural consciousness as a landmark event in humanity's ongoing dialogue with the cosmos. The psychological effect on humanity is difficult to measure but easy to sense. Unlike distant supernovae or quasars, whose events unfold millions of light years away, this collision will happen within the neighborhood of our own solar system. That proximity makes it feel tangible, immediate, and personal. When telescopes capture the moment of impact, millions may watch live, experiencing the cosmic collision as a shared global moment. It will be a unifying spectacle, reminding humanity of its common home under one sky. Just as the first images of Earth from space reshaped perspectives, so too may the vision of another planet being struck by an interstellar traveler alter how people view their place in the universe. Among exoplanet researchers, the collision sparks curiosity about parallels elsewhere. If interstellar objects can collide with Mars, they can collide with exoplanets orbiting distant suns. Such impacts could deliver water, organics, or heavy elements to young planets, influencing their habitability. Observing 3I Atlas's impact on Mars offers a microcosm of galactic processes that may shape countless worlds. It becomes a demonstration that cosmic traffic between star systems is not just hypothetical, but actively ongoing. Every planetary system is part of a galactic ecosystem in which bodies are exchanged, sometimes violently, across stellar boundaries. Mars, in this sense, is becoming a visible example of a universal principle. Worlds are never entirely isolated, and their stories intertwine with the greater galactic narrative. There's also excitement about how the event might affect ongoing robotic missions. Current rovers like Perseverance and Curiosity may not be in direct view of the impact, but their instruments could still register indirect effects. Seismometers may detect vibrations, cameras might capture dust hazes, and atmospheric sensors could note sudden changes in pressure or temperature. Even orbiters not initially designed for high-speed plume observations may adapt their missions to capture data, demonstrating the flexibility of human ingenuity when faced with the unexpected. The event highlights the importance of maintaining a diverse fleet of instruments across the solar system, ensuring that when the cosmos presents an unplanned experiment, humanity is ready to watch. The broader astronomical community, too, sees in this event a chance to refine public engagement. Rarely does a cosmic event align so perfectly with public interest, scientific importance, and observational accessibility. Astronomers know that engaging the global population with the spectacle could inspire a new generation of scientists. The drama of a planetary collision, combined with the exotic allure of interstellar material, provides a narrative that transcends technical jargon. It becomes a story of discovery, danger, and wonder, capable of drawing children, artists, educators, and dreamers into the fold of scientific curiosity. The legacy of 3Y Atlas may thus extend beyond data, shaping the culture of science itself. Speculation has even arisen in some circles about whether the collision could trigger secondary processes within Mars. Some wonder if deep ice reservoirs might melt, producing transient flows of water. Others consider whether buried carbon dioxide deposits could sublimate, thickening the atmosphere in patches. While these ideas remain untested, the mere possibility electrifies planetary scientists, as it hints at ways impacts could temporarily alter planetary habitability. Although no one expects Mars to become Earth-like overnight, the event reminds us that planets are dynamic systems, subject to sudden jolts that can reset their environmental conditions. These moments of flux may hold keys to understanding how habitable environments arise, evolve, or vanish. The ethical dimension of studying such an event also emerges. While no humans or ecosystems exist on Mars to suffer harm, the deliberate act of closely observing a catastrophic event still raises questions about the human relationship to destruction. Some critics suggest caution in glorifying a collision that represents massive planetary devastation. Scientists counter that observing natural cosmic processes is not exploitation, but participation in understanding a reality far larger than human influence. Still, the dialogue highlights an important tension in how humanity interprets cosmic violence, as both a source of knowledge and a humbling reminder of fragility. The impact becomes a mirror reflecting not just the universe, but also human values and perceptions. The revelation that an interstellar body will meet its fate against the surface of Mars continues to send ripples through multiple communities. But the sheer scale of implications stretches further still. It is one thing to observe an unusual comet streak across the sky, and another to witness a fragment of another star system crash into a world that humanity has long regarded as its next frontier. The layers of meaning and consequence are vast, and even after the outpouring of analysis, entire new directions of thought unfold when considering what this means for the present and the future of human understanding. One of the most fascinating aspects of this event lies in the realm of comparative planetology. For decades, scientists have used Mars as a proxy for early Earth, pointing to its ancient riverbeds, deltas, and dried lake beds as evidence that it once shared traits with our own planet. The impact of 3Y Atlas provides an extraordinary opportunity to see what happens when a massive external force interacts with such an environment. Earth itself has been reshaped many times over by great impacts, but time, weather, and tectonics have hidden much of that record. On Mars, where processes move slowly and surface features endure for eons, the new scar will be preserved with clarity. Comparing the aftermath to craters here on Earth could recalibrate models of planetary surfaces and help untangle mysteries about Earth's earliest epochs, when colossal collisions may have played roles in creating oceans or seeding chemistry vital to life. From a broader astrophysical perspective, the event emphasizes the interconnectedness of stellar systems. For so long, astronomy has divided its subjects into categories: our sun and planets on one side, distant stars and galaxies on the other. Interstellar objects blur this line. They are tangible evidence that matter is exchanged between systems, flung outward by chaotic encounters and wandering until captured by new gravitational fields. When one of these wanderers collides with a planet, it demonstrates that planetary histories are not confined to their birth stars. Mars will now incorporate into its story material from across the galaxy, as though two distant family trees have suddenly entwined. The cosmological implication is profound. Planetary identities are porous, and their geologies can become composite records of galactic mixing. Philosophers of science have also seized on this theme. Some argue that the impact forces us to rethink our notion of planetary sovereignty. We often speak of Mars as a discrete, self-contained world, yet after this collision, it will bear matter from beyond, not just its planet, but its star. In a way, Mars becomes a hybrid, a site where galactic histories overlap. The boundary between our solar system and the galaxy beyond becomes less rigid, replaced by the recognition that exchange and interaction are universal. This shift in thinking could influence how humans conceptualize planetary systems elsewhere, not as sealed capsules of history, but as nodes in a vast interconnected network of cosmic exchange. For those engaged in the search for life, the event inspires both excitement and curiosity. One of the great debates has always been whether interstellar bodies might carry complex organic molecules, or even prebiotic compounds, that could seed planets. Known as panspermia, the idea suggests that life or its ingredients might travel between stars embedded in comets or asteroids. With 3I Atlas, we gain a rare test of this hypothesis. When the body collides with Mars, heat and pressure will obliterate much of its structure, but not necessarily all of it. Some fragments may survive intact, buried in ejecta fields or fused into glassy impactites. If these fragments contain organic molecules distinct from those found in the solar system, it would be a powerful hint that the galaxy as a whole is seeded with building blocks of life. Such evidence would suggest that the story of biology is not isolated to Earth or its near neighbors, but is written across countless stars. Another dimension often overlooked is the role of time in shaping the significance of the event. Impacts have always been part of planetary history, but humans have rarely had the means to predict or observe them in real time. What makes this collision unique is not just that it is happening, but that we know it is happening in advance. The foresight allows for deliberate preparation, careful planning, and systematic observation. In essence, humanity has matured to a point where it can witness cosmic violence not as helpless bystanders, but as organized investigators. The ability to marshal fleets of telescopes, satellites, and landers to capture every second of the process demonstrates a new stage in the relationship between intelligence and the cosmos. It is a moment where the universe is not just experienced, but studied, where awareness allows humanity to transform chance into knowledge. The artistic imagination has also been stirred in ways rarely seen with astronomical announcements. Painters, filmmakers, and writers have long envisioned planetary collisions, but those were speculative, woven from fiction and fantasy. Now, with a real interstellar object on course for Mars, creativity finds itself infused with actuality. Visual artists imagine the red planet lit by the sudden bloom of impact, clouds of dust billowing into the thin air, a horizon altered forever. Writers explore themes of destiny and cosmic inevitability, framing the event as a symbolic meeting between worlds. Musicians even compose pieces inspired by the idea of a galactic traveler striking down upon a planet that has haunted human imagination for centuries. In this way, the impact becomes not just a scientific milestone, but a cultural one, embedding itself in the shared human narrative. Even within the scientific community, unexpected fields find new relevance. Astrobiologists studying extremophiles, for instance, wonder what microbial life could endure such cataclysms if they occurred on inhabited planets elsewhere. Geochemists consider what rare mineral phases might form under the extreme pressures of such an impact, phases perhaps never seen in laboratories. Astronomers interested in exoplanet atmospheres imagine the signature such a collision might create if observed from afar. They speculate on whether alien civilizations, watching from light years away, might already be aware of similar collisions shaping worlds around their stars. The event becomes a template for extrapolation. By studying it here, humanity learns what to look for in the endless field of exoplanets beyond. On the pragmatic side, the collision also influences how future missions are prioritized. Agencies that once debated the relative merits of lunar exploration, asteroid mining, or Martian settlement now find themselves compelled to refocus on Mars, if only to capitalize on the unique scientific windfall the impact will provide. Funding proposals suddenly seem more urgent, as the opportunity to investigate fresh interstellar debris is unlikely to recur soon. International cooperation may deepen, with spacefaring nations pooling resources to ensure comprehensive coverage of the aftermath. Even private companies, who envision Mars as the eventual home of human colonies, are forced to reckon with the fact that nature itself will alter the terrain before they arrive. The surface they plan to colonize will not be the one they originally studied. Educational initiatives are already being shaped around the impending event. Schools and universities recognize that the drama of a planetary collision can inspire interest in physics, astronomy, and planetary science in ways textbooks alone cannot. Curricula are being adjusted to highlight the processes at play, from orbital dynamics to shockwave propagation. Students are being given opportunities to participate in citizen science projects, tracking the object or modeling its impact. This democratization of the event ensures that the knowledge and excitement will not be confined to elite institutions but spread widely, planting seeds of curiosity in minds worldwide. Generations from now, some of the scientists studying the crater on Mars may trace their careers back to the awe they felt as children watching 3I Atlas descend. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on NASA's warning about 3I Atlas colliding with Mars? We want to hear from you. Thank you for watching and see you next time.